Hello, my name's Karl Egeland-Eriksen, and I've put together a few slides just to outline the content of the course that I'm going to be running for the Natural History Society on oceanography. The course starts at the end of this month and will run for 7 weeks, Fridays between 10 and 12 via Zoom. The subject of oceanography is quite complex, but can be conveniently divided up into different scientific disciplines of physics, chemistry, biology and geology. So we shall look at the geology of the ocean basins, the ocean floor, the chemistry of seawater, the physics of ocean tides and currents, and the biology of the marine life and the interactions between those various different areas. So week 1 we'll have a brief introduction on the history of oceanography, the early navigators, cartographers, and how they mapped the coastlines and things like that, onto the earliest proper sort of extensive research of the oceans, which was carried out during the Challenger expedition in the 1870s, where they did numerous experiments and sampling and measurements of salinity, currents, depth, marine life, ocean sediments, all those sorts of things. And that really signalled the birth of oceanography as a science as we sort of understand it now. The Earth's crust is divided conveniently up into continental crust and oceanic crust. The oldest rocks on the planet are over 3.5 billion years old, and they are all found on the continental crust. The oceanic crust is younger generally than 200 million years. There's small areas where it's a little bit older than that, but the vast majority of the oceanic crust is only 200 million years old, which is a fraction of the lifespan of the Earth. Oceans have been present on the Earth for a lot longer than that, but the current ocean basins are all relatively young, so we'll look at why that is. And we'll look at the structure of the ocean floor, the ocean basin, from the continental shelf down the slope to the abyssal plains of the deep ocean, to the mid-ocean ridges where crust formed, and to subduction zones and trenches where the ocean crust is destroyed, basically. And we'll look at the geology, the rock types that make up the ocean floor, how they form, where we find them, and also how the deep ocean seawater penetrates through the permeable oceanic crust and is cycled by hydrothermal systems which add minerals and then remove them when the water emerges from black smokers, white smokers, warm water vents around the area of the mid-ocean ridges. And we'll look at the history of sea level through time. We're worried about global warming and climate change and rising sea levels of a couple of meters or so, but if you look in geological time, we've had sea levels much higher than the present day, so we'll discuss that. And also we'll discuss how the ocean currents have changed over time, largely due to the shifting continents and blocking off passageways for the currents, and we'll look at that as well. Week 2 we shall switch to a bit of chemistry and physics, looking at properties of seawater and also the chemistry within them. We'll start with a bit of the global water cycle and look at the physical properties of water, and it's those properties which are essential really for life on Earth. Ice floats on seawater, and without that we would have great difficulty surviving the ice ages and snowball Earth periods, because the entire ocean would freeze if the ice didn't float. So we look at what the composition of sea ice is, relative to seawater, see what effects that has. We'll look at global seawater surface temperatures. It's hotter at the equator and colder at the poles, as you'd expect. But we'll also look at the variation in temperature through depth down to the deep oceans, where it's about 4 degrees C. We'll also look at water, the salinity of seawater. It varies throughout the globe, sometimes locally, sometimes quite extensively. So we'll look at the changes in salinity and causes for that. And we'll look at that distribution of salinity, how it relates to the continents, river systems and things like that. So we shall look at that. And we'll also look at density of seawater, how it changes with depth, and salinity changes with depth, along with the temperature, which we discussed just earlier. And we'll also look not only at the surface currents, but the real deep water currents there, where the cold water forming in the polar regions sinks to the depths of the ocean and then circulates along the ocean floor, coming up and warming eventually to replenish the surface waters before circulating back to the start, basically. So we'll look at that system. Light doesn't go right the way through seawater. It has a limited ability to penetrate seawater, and it varies the wavelength that penetrates. Differs in both coastal areas and deep ocean areas. Blue wavelengths penetrate the deepest in the open ocean, whereas in coastal waters it tends to be the green part of the spectrum, so we'll look at why that is. And also, sorry about the quality of this slide, but we'll look at the passage of sound through seawater. And this particular interesting zone called the sound channel, where sound seems to travel long distances confined within this zone. And as the picture indicates, it's popular with things like whales, because whale song will travel further in this zone than in deeper waters or shallower waters. So we'll look at that. Composition of seawater, obviously it's mainly water, but with salts in it, and we'll look at how the salinity varies over the oceans, across the oceans, and we'll analyse the salt part of the seawater and break it down into the various different elements and compounds that make up the salt side of things. And also the ocean has an interaction with the atmosphere, oxygen, carbon dioxide, things like that. So we'll look at that too. Okay, week 3, a bit more of the physics, where we'll look at the ocean circulation and also atmospheric circulation, since the two are linked. The solar radiation drives these atmospheric systems, which create the winds. The rotation of the globe deflects those, and it's the winds that drive the friction on the ocean surface that creates the waves and the currents. So we shall look at that. And we'll look at the various different surface current systems that we have. In particular, attention to the North Atlantic gyre of the Gulf Stream and the North Atlantic current, the one that affects us most. But also looking at the wider global surface circulations, which are particularly important in current times in terms of pollution. It's the centre of these gyres where the plastics and things tend to accumulate over time, because there's less motion in these central bits than there is around the outer sides of these gyres. So that's the ones we see in the news, with all these plastics building up in the North Pacific and things like that. So we'll look at that as well. Again, we'll look at the deep currents and how they flow around and how they affect the presence of life in places because of the movement of nutrients and things along those pathways. We'll then move on to the coastal areas in the following week, where we shall looking at waves, tides and things like that. So what are waves, how are they formed, how deep do the effective waves go, and then we'll look at the tides, the interaction of the sun, the moon, and the earth and the oceans, and why the tides aren't the same everywhere. And then we'll look at how sediment enters the seawater from the land, where it's deposited, what influences that, particularly in this littoral zone between the head of the beach and to where we call the offshore zone. Okay. And we'll also look at mudflats and things like that, and also estuaries, and what happens when fresh water enters the sea and how it's affected, the distribution is affected between incoming and outgoing tides and things like that. Also at deltas, a major system for sediment entering the oceans. And then finally we'll look at the continental shelf. The light blue areas on this map shows you the areas of continental shelf, which are made of continental crust overlain with sediments. So we should look at those areas. Following week we'll go look at the opposite end of the spectrum, the deep waters. We'll look at how sediments form and how they vary across the globe, what these sediments are made up of, and why they're distributed the way they are. And the whole cycle from photosynthesis, phytoplankton, the whole food chain, movement of carbon through the oceans, so you get this snow falling, this material falling, forming the deep ocean sediments. And then we'll look at how various minerals, the shells of an awful lot of organisms, skeletons in the ocean, are made of calcite or calcium carbonate. Others are made of silica. Now those two minerals behave differently in the seawater. Calcium carbonate isn't stable as it gets colder and deeper in the oceans, and it dissolves. So we don't find limestone forming in deep waters because it's too deep, too cold, pressure's too great. Silica, on the other hand, which also makes up the shells and skeletons of some marine organisms, behaves differently. So we'll have a look at that. And then we'll look at how sediments arrive on the sea floor, mainly from the ocean, the continent rather, down the continental slope with things like turbidity currents, but also things like drop stones, which are stones that material that's within icebergs, but as they melt it then deposits those which end up on the seafloor as well. So we'll look at those sources of sediment on the seafloor. Sorry for this blurry slide as well, but this is a look at the chemistry going on in the sediments on the seafloor. So the deep ocean at the top of the slide, and then the very surface sediments have oxygen in them, they're oxygenated, but as you get deeper you get to anoxic areas, and there's different chemical processes going on in there, so we'll have a look at that. And then following week we'll get on to the biology of the ocean, and we'll look at various different classifications of the life in the ocean, and the different zones that they occupy. The specialised to these zones, the phytoplankton and the zooplankton, which basically, although the zooplankton have a little bit of mobility of their own, they're generally moved around by the currents, whereas the next lot, the bigger animals, the nekton, they can swim against the current. And then right at the bottom we've got these ones that live on or in or close to the deep water, to the sea floors. Those are the nektons. So we shall look at the surface organisms, these planktons, nektons, and the benthos, these species that live at depth, and also how these benthic communities interact. And in the final week we will look at the interests of man, humans on the ocean, We'll look at what we use the oceans for, what we get from the oceans, and we shall look at how different parts of the ocean are assigned to different countries in terms of who's allowed to exploit them, things like the exclusive economic zones. And then also look at the United Nations Convention on the Law of the Sea, which tries to govern these things, and which countries haven't signed up to that. The ones in red on that map, so we'll look at the reason behind that. And then we'll take a look at a couple of sort of case studies. At the moment I've got down the Arctic Ocean as one of them. As the polar ice cap melts, it makes this polar region far more accessible, and so which countries have rights to what in that area. We'll also have another look at a different case study, which will look at the Galapagos Islands World Heritage Site and see why they are so unique, and what's going on in terms of the oceanography in that area. Okay, so that's a brief summary of what we'll be covering in the course, and if it's of interest to you, there's still some spaces available, so if you want to sign up for that, details are on the NHSN website, and I look forward to seeing you in a couple of weeks for week 1. Okay, bye for now.